Hello deep learners, welcome to this fourth lecture of PyTorch 0 to Hero playlist where we are going to build and train a neural network from scratch. So here we are going to do it in a manual way. We are not going to use NN or Optim. Then we are going to learn about the NN and Optim modules which PyTorch provides us. And lastly, we are going to use this NN and Optim to improve our neural network building and training process. And also, it will be packed with lots of coding and practical implementations. So take a pen and paper, grab a hot cup of coffee, and let's get started. Alright guys, so it's time to build our first neural network inside PyTorch. So here, we will build it in the old school method, which means that we won't use the NN module or the Optim module. We will just use our pure logic and maths and build the neural network. So let's go. Alright guys, now let's talk about the workflow, like how we are actually going to execute this. So I'm listing the steps over here of what we are going to do in this manual pipeline, and we'll go through each one by one. So at the very first, we have our data set. So here, first we get our data set. So this is the first step, and inside this, we first get our data set from Kaggle or from any other sources, or we generate our data set. How? Basically, we can generate data set using a scikit-learn functions like make classification or make regression. So these, they come from our scikit-learn, which is known as sklearn. Alright, now once we got our data set or we generated it, the next step is to clean this data set. So this cleaning, it includes removing the junk, filling the missing values, replacing the duplicates. So here we basically clean our data set so that we can work on it efficiently. And in the next step, we perform the train test split. Meaning if this is our data, then suppose 80% we may convert it to our train data, and the rest 20% we make it the test data. So it is an 80-20 split between the train and the test data. So we split it. Next we scale the data. We scale it so that neural networks can understand the values. Because innately they cannot understand absolute values. Therefore, by scaling, we make it zero mean and unit variance. So that our neural networks can understand this number, or they can understand this data set, and they can work on it efficiently and they can get trained on it. And the last step includes, so this whole process, it is basically done on NumPy arrays, but we want to work in PyTorch. So this fourth step includes converting our NumPy arrays to our torch tensors, right? And that is it for the first step, which is my data set. Alright, now let's talk about the second step, which is modeling. So here is where we create our neural network class, and we do it manually because we are first seeing it in the manual way. And we will do it by basically creating weight and bias matrices. So we'll do that because we'll code in the next step. And these weight and biases will be basically tensors, right? And in the next step, what we do is we define parameters. What are these parameters? These parameters include our learning rate, our number of epochs, our weight decay suppose, and also we specify our loss function. So if you are working with binary classification problem, we use the binary cross entropy loss. If you are working on multi-class classification, we'll use the only cross entropy loss. If you are working on in a regression problem, we'll use MAC or MAE, which stands for mean squared error, and it stands for mean absolute error. And in the third step, we basically train our neural network, and this is the crucial step. So here we train our neural network. So first over here we had our model or our neural network class. So basically we create an object of that class. So we create an object and we call this object our model or our neural network, right? Next we run a loop for epoch number of times. So it runs from 0 to epoch number of times, which was our n of epochs. And for each epoch, first we do forward pass. Next we do loss calculation. Next we do gradients calculation. Next we do parameters update. And lastly we do zeroing out gradients, or you can say clearing out gradients, so that we don't accumulate it in the next step, right? So that's why we clear it out. Alright, so first over here we do forward pass. So in this forward pass, what we do is we get our y hat as model of x. So this is our model, which is this. This is our input and this is our predicted output. So we pass our input to our model and we get our y hat, right? And next we do loss calculation. So we have our y, we have our y hat. What is y? It's our actual output and this is our predicted output. So we calculate the loss using our loss function. So suppose this is a binary classification problem. So we have the binary cross entropy loss function, and to that we pass our y hat and y. Next we do gradients calculation. Means here we calculate the del L by del W and del L by del B. What are this? This is the loss gradients with respect to my parameters. And these parameters are nothing but my weights and biases. So here I am calculating these gradients, and lastly I am updating my parameters using gradient descent. So you know the logic, it's weight equals weight minus eta times del L by del W, and B is equals to B minus eta times del L by del B. So here I am updating my parameters, and finally I am clearing out my gradients. Why? To prevent my gradient accumulation errors, right? To prevent my gradient accumulation error. And that is this whole training process. And in the final step, or in the fourth step, we do evaluation on test data. So you can say we do inference. Meaning what we do over here is that we give our model new unseen data. So here we pass the X test, which is the new unseen data, to our model. So we pass it and it gives us our y hat. And this is the predicted output on this test data. And once we got this y hat, which is new unseen data, we basically see how good is this predicted output on this test data, which is new and unseen data which has not been fed to this model during this training process. So if the model actually learned in a good way during the training, then obviously it will produce good outputs on this test data also. And if it's predicting well then you have built your first neural network without using any black box like NN modules or your Optim modules, right? You have just used pure logic like all this logic and you have coded your neural network, and yeah, kudos to you. Alright guys, so now that we have seen all this workflow and this manual pipeline, let's actually go to Colab and code it, because that's how things will really make sense, right? So let's go. Alright guys, so let's start coding. So at the very first, we import our packages, and here we are importing our Torch. We are importing NN and Optim from Torch, although we didn't use here, but still we are importing. We import the make classification because we are generating a synthetic data set. We're importing matplotlib because we want to plot graphs to see how our data is actually looking. Alright. Next we import NumPy because our data sets will be represented as NumPy arrays, which will later convert into PyTorch tensors. And lastly, we import the train test split from scikit-learn model selection, and this train test split helps in splitting our data into training and testing. And lastly, we import standard scalar and label encoder from scikit-learn processing, and we use this standard scalar to scale our data so that they have a zero mean and a unit variance, so that our neural network can understand these numbers and actually learn and get trained efficiently. Next, we are getting the device using torch.device of CUDA if torch.CUDA is available, else we are using CPU. And if I print my device, you can see it says CPU. So that means I'm not using my T4 GPU, I'm using the normal CPU inside Colab. Next, we create our dataset. So here we use the make classification function from scikit-learn to generate a synthetic dataset for classification task. So here I have given n samples as 500, which means total data points, there will be 500 of them. And I've given my n features as 2, meaning the number of features used will be 2. And then n informative is 2 and n redundant is 0. Alright, so that's basic stuff for creating a synthetic dataset. And next I'm plotting it. So this is our dataset, our bandit classification dataset. So here is how it looks. So this is my feature 1. As you can see, because n features is 2, we have 2 features. So I've named it the feature 1 and feature 2. So this is feature 1 and this is the axis along the feature 2. And you can see these are the 500 data points that has been plotted. Now this is returning our x and y. Now what is x? X is my features and y is my labels. Now simply because n features is 2, the shape of x is 500 cross 2. This 500 is the number of data points and this 2 is nothing but the number of features. So we have 2 features, that's why here we have 2. And y dot shape, y is basically the labels or the target. So you can see because there are 500 data points, it's just 500, right? And these are, if you do type of x and you do type of y, you'll see these are NumPy arrays. So that's why we imported NumPy at the very first. Now if you do np.unique y, you can see in our labels, we have only 2 unique values which are 0 and 1, which obviously makes sense. Why? Because it's a binary classification problem. Alright, next we do the train test split. So we use the train test split that we imported from scikit-learn.model selection. And then here we pass our features and our labels and we give the test size as 0.2, which means there will be a split of 80% and 20%. Why? Because this test size, so suppose the whole data set is 1, alright, it's 1. This test size basically tells how much will be my test data. So here I've mentioned as 0.2. So automatically my train data will be my 1 minus 0.2, which is the remaining, or it's 0.8. So you can say that's why that this train test split is basically a 80-20 split over here, an 80% and 20% split over here. Alright. And then we are getting the train data and the test data for features and labels. And then if you see the shape of xtrain and xtest, we see it's 400. And if we do ytrain.shape and ytest.shape, we see it's 400 and it's 100. Because total data points we have as 500 and we are using 0.2 times, meaning 20% of our data set for our test data. So that is 100. So that is why you are seeing here that for test data we have 100 data points. And for the train, we have the 500 minus 100, which is 400. Alright, now we scale it. So we use the standard scaler And then this is the syntax. So we first scalar dot fit transform on the train data, on the train features, and then we do scalar dot transform on our test features. So it basically scaled the values on our features, and you don't apply it on the label, right? So as you can see, it's NumPy arrays. Now the last step was to convert our NumPy arrays to our tensors so that we can work in PyTorch, and that is what we are doing. So xtrain is equals to torch.tensor xtrain. We are passing this only, which is this NumPy array, into this torch.tensor, and we're specifying the device as this, which is the device which we first created, this one, right? And similarly we do the same with the xtest and ytrain and ytest. So if you do xtrain.shape, xtrace.shape, you get to see that it's a tensor, right? It's torch.size, meaning it's a tensor, right? You can also see the data type. So it's float 64. And if you do type of xtrain, yeah, it's torch.tensor, meaning we have converted our NumPy arrays to our torch tensors. And lastly, we are changing our data type from float 64 to float 32. So xtrain is equals to xtrain.to torch.float32. And we are doing the same with test and ytrain and ytest. So we are converting all to float 32 data type. Now the second step is the modeling. So here, this is our neural network class which I told you guys. And here we have two functions. First is the underscore init method, and next is the forward method. So this underscore init method, what it's doing is it's basically initializing my weights and biases. So it initializes the weights and biases. And how is it doing? You can see self.weights is equals to torch.rand. So remember the tensors lecture. Torch.rand is used for random initialization, right? So here we are randomly initializing values, and then we mention here the size. So the shape or size is this. Now what is x.shape of 1? So this x.shape of 1 is nothing but our number of features, which is 2, right? Why? Because we have two features, f1 and f2. That's why x.shape of 1 is 2. Simple. So this weight matrix is a tensor of size 2 cross 1, and we're using the data type as float 32, and we are doing requires grad as true so that we can compute gradients whenever required. And lastly, we pass the device as device so that this weights is present at this same device which we are using throughout this whole collab. And the same we do for bias, but here we use the torch.zeros, which basically does zero initialization. And then we have this forward method, which is nothing but it is doing the forward pass. So here we first take our x and we calculate z, which is w times x plus b. So this is nothing but it's this, right? So it's x at the rate of my weights, and it is a dot product, and with that we're adding our bias, and that gives our z. And then we calculate our y hat as y hat, or my y pred is nothing but my sigmoid of z, and that is what we are doing over here. And lastly, we are returning this y hat or this y pred, which is nothing but my prediction, right? Or this is my predicted output. So we define this neural network class. Then we define the training parameters like the learning rate, which is also known as eta, which is used in the backpropagation algorithm in the gradient descent whenever we are updating our parameters. And we have our number of epochs as 25, so that training loop will run for 25 times. And next we create our model or our object of this class, and here we pass the xtrain So this xtrain goes over here. Alright, and that will basically give our model. So we can access the model's weights and biases using the model dot weights and the model dot bias. And you can see that the data type is torch.float32. Now if I do the same, but if I see the shape, so if I do model dot weights dot shape and model dot bias dot shape, it tells me that the weight is of shape 2 cross 1 and the bias is of shape only 1. So that is our weights and biases of our neural network. And then we have our BCE loss, which is loss equals to minus of y log of y hat plus 1 minus y times log of 1 minus y hat. And we have put this minus sign outside so that we don't have to put it minus and again minus over here. We are just putting all that inside a bracket. And then we are computing its mean. But before that, we are doing this thing, which is basically clamping, meaning our ypred, it is basically clamping all the values from this range to this range. So that any value is, if it's less than epsilon, it will basically become this value only. And if any value is greater than this number, then it will become this number only. So here we are doing epsilon, but it's not required. And lastly, this is our training loop. So we run it for n number of epochs. So it is run the loop for n number of epochs. And in each epoch, we are doing our forward pass. So model dot forward of xtrain. And what it's doing is, it's first calculating our z, then it's calculating the ypred. And it is returning this ypred. And we are storing it over here. And next we calculate our loss. So loss equals to BC, this function, and we pass the ytrain or the actual output over here, and we pass the ypred, which is coming from this forward pass, and it is going over here, and we are doing this formula, and it is returning loss, and that loss is coming over here. Simple. And then we do gradients compute. So this is my gradients compute. And what are these gradients? These are the loss gradients with respect to my weights and biases. So basically it is going backwards through the computation graph and it is computing the gradients with respect to weights and biases. And once we got the gradients of loss with respect to weights and biases, we are basically updating our parameters. So model.weights is equals to, so it's weight is equals to weight minus eta times, or my learning rate, times my gradient. And this gradient is nothing but the derivative of loss with respect to my model weights. And the same we do over here, which is nothing but it's just bias equals to bias minus eta times grad. And this grad are different. This grad is loss gradient with respect to weight. This is loss gradient with respect to bias. And this is how we are updating our parameters using the gradient descent algorithm. And then we are clearing out gradients so that in the next step, we don't end up actually accumulating these gradients, but we are starting fresh. And that is the accurate representation of our gradients. And this is very crucial step. And at the end, we are basically printing our loss. And this is how we are doing it. So if we simply run it, you will be able to see that we have run instantly for 25 epochs. And this is the loss in every epoch. So you can see that the loss is minimizing, meaning it is converging, right? And that is how training is actually done. And in the final step is our inference. So here we feed our model new unseen data which was not fed during the training, and we see how good its predictions are. So with torch.no gradient, so we are disabling the gradient tracking, meaning that while inference or while evaluation, we don't want any gradients to be computed, right? We just want to do the forward pass and we want to check how good are these predictions. We don't want any gradients to be computed. So that's why we do this. And then we do the forward pass so that we get this. And as you remember, I told that the sigmoid value, it basically squeezes all the values and brings it into a range of 0 to 1. And if any value, if it's greater than 0.5, then it's 1. And if any value is less than 0.5, it is 0. Right? So that is what we are doing. Y-test spreads is equals to greater than equals to 0.5. Meaning that if any value is there which is greater than equals to 0.5, it will become 1. Else it will become 0. So again, this is y-test spreads is storing nothing but my zeros and ones. And simply we got the accuracy by doing this equality check where we are doing y-test is equals to y-test spreads, this one, dot float dot mean. So see, our y-test has two values 0 and 1, and our y-test spreads has also two unique values 0 and 1. So what this accuracy is calculated is, we are checking the equality and we are doing mean. And what is mean? Mean is nothing but sum divided number of terms, right? Alright, so let me explain it. So let me say that my y-test looks like this, 0, 1, 0, 1. But my model actually predicted this 1, 1, 1, 1. Now y-test is equals to y-test spreads will come out to be, so 0 and 1 is not equal, so it will come 0, 1, 1 are equal, 0, 1 is not equals, 1, 1 is equals. So it will come something like this, right? Now if we calculate the mean, it is nothing but the sum of these terms. And what is this sum of terms? It is basically 2 divided by the number of terms, which is 4. So it will come 0.5. So I think you got the idea. So here we are getting the accuracy as 0.5, and that is very clear because our y-test spreads, it basically out of 4 predictions, it did 2 predictions correctly. That's why it has 0.5. Now if I do the same, but now let's suppose this is my second case. Let me say that it is this, and let me say that it actually predicted it correctly, everything. Then this will become all ones, and then if we calculated the mean, it will come nothing but this, and this will result to 1, which is 100% accuracy. And that is what is the intuition of this line. So with this, we're simply able to see how accurate our predictions are. And if we execute it, and we're getting an accuracy of 0.5, which is very bad, because an accuracy of 0.5 actually means that it is doing a random guess, right? So every time it is doing a random guess, and that is very bad. But we'll see in the future lectures how we can improve it. But for now, this is the manual work line. Now let's learn about NN and Optim modules so that we can optimize this pipeline and make it much more faster and efficient. Alright guys, so now that we have seen how the manual pipeline works and how to code it, let's have a look at the NN module. So this NN module is basically a PyTorch model which makes the process of building neural networks much easier and much more faster. How? So actually this NN module, it provides us predefined layers, activation functions, loss functions, so that we don't have to manually code as we did. So we don't have to do that from scratch. So we can use this pre-built stuff and make the process much more faster. And trust me guys, these layers, activations, loss functions which are provided by our NN module are highly optimized. So they are much better than ours which we just coded right now. And also this NN module, it lets us code our neural network in an object-oriented manner, meaning that we can make it modular so that its structure is better organized and we can easily debug it and maintain it over the time. And this NN module, it simplifies the whole model building process because here we don't have to manually handle and create our weight matrices or our bias matrices. They all handle it under the hood by their own selves. And here also we don't have to do the forward pass by ourselves. Like at first we computed the Z and then we computed the Y hat. Here it is all done under the hood automatically. And that is the beauty of NN module. Moreover, it handles the errors, it handles the tensor operations, gradients, shapes very accurately, because if we had to do it, then probably it would be much more error prone, right? Because we are humans and we can do some mistakes, but these are highly optimized and these are created by very intelligent people, so definitely we can trust on them. And using this NN module, we can easily build deep neural networks with much more complexities and which can easily scale over the time. So just to reiterate, this NN module, it provides us layers like linear layers, batch normalization layers, layer norm, RMS norm. It provides us convolutional layers, max pooling, LSTM layers, RNN layers, and much more. Next, it provides us activation functions like ReLU, sigmoid, tanh. It has loss functions like binary cross entropy loss, which are used in the binary classification problems. It provides us cross entropy loss, which we use in the multi-class classification problem. It gives us MAC loss, MAE loss, which are generally used during regression problems. And also it has some containers like sequential, module list, which are basically used for stacking multiple layers. And that makes organization much more beautiful. And that's the beauty of the NN module, which PyTorch provides us for building neural networks in a much more beautiful manner. Alright, now let's look at the Optim module. So, in the backpropagation algorithm, after we have calculated the gradients of loss with respect to all the weights and biases, we simply update these weights and biases using our gradient descent logic, right? And we did it manually. But this Optim module is another PyTorch module which provides us optimization algorithms which handles updating this model parameters like our weights and biases automatically. So here we don't have to manually code our gradient descent logic. Instead, this optimizer takes care and it does the updating parameters by itself. And that is the beauty of Optim module. So basically it automates the parameter updates so that we don't have to manually implement it. And also it provides us advanced optimization algorithms like SGD, ADAM, RMS prop, ADAGRAD, energy, momentum, which not only do gradient descent, but also they do some more advanced techniques which makes our training much more stable and much more faster. So that's why instead of manually coding the gradient descent logic, we should use the optimizers provided by this Optim module. And this improves our efficiency as compared to the manual coding. So that is the idea of Optim module provided by PyTorch, which makes the process of updating neural network parameters much more easier so that we don't have to do it manually. Alright guys, so now that we know what is NN and Optim modules, let us see how we can optimize our pipeline using these. So let's go. So first, instead of manually coding our neural network from scratch, we basically use this NN module for building our model. So here we use its predefined layers, activations to create our layers and to organize them in a better structure. And that's why this model becomes very scalable and also easy to debug whenever we are revisiting it in the future. Next, instead of defining our own loss, we use the loss provided by NN module. Like it provides us BCE loss, cross entropy loss, MAC loss, MAE loss. So why should we define our own loss when it is already providing it? So simply we use them and make the process much more faster. And these loss functions provided by the NN module, they also support AutoGrad. So we don't need to worry. We just calculate our loss and we just do dot backward and we get the gradients of our loss with respect to all the parameters in the neural network. So that makes the whole process again much more faster. And finally, instead of writing our own gradient descent logic, we use optimizer module and we use one of its optimizer like atom, SGD, RMS prop, energy, momentum, anything to simply update our neural network parameters so that we don't have to take the stress of it. Instead, we let it to handle it efficiently. And trust me guys, it does it beautifully. Now guys, let's go to our Google Colab and optimize the manual pipeline using our NN and Optim modules. So let's go. Alright guys, so this is the code for NN modeling. So at first, we, instead of using our own neural network class, we use the NN module. So we first define our class like this. So class this, and then over here, earlier we had like this, but then we do this. So we pass the NN.module over here. And then we create two functions, init function and this forward function. And inside this init function, we have self and we have num of features. So you can see that it is very much like oops. So simply it's the concept of inheritance only. And inside this init, at the very first, we do this so that we are calling the init function of this superclass, which is NN module. Alright. Next, we define our model. So this is our model. So define our neural network. And here we are using the sequential, which is coming from NN. So if you remember, we are importing NN and Optim from Torch, right? So from Torch, we're importing NN and Optim. And here we're using this NN and we're using the sequential. So this sequential is used to stack multiple layers on top of one another. So in NN, we have multiple layers like linear layers, convolutional layers, RNN layers, RSTM layers. And using the sequential, we basically stack them one after another as if we are grouping them. So self.network is equals to NN.sequential and we are passing these. So what are these? So this linear layer is nothing but your hidden layer. So at the very first, my num of features is 2. Now this is the first. So NN.linear, num of features, which is 2 to 16. Means that if I have my data like 500 cross 2, from here, you can think that it's something like this. 2 cross 16, right? So this linear layer is taking 2 as the input and projecting out 16 as the output features. So this will basically be your 500 cross 16. Next, we are passing this output to this NN.ReLU. So in sequential, the output of one layer is passed as input to the next layer, right? So this output is passed to this ReLU, and this ReLU is nothing but a activation function, which I hope you all guys know. So here we got 500 cross 16. Next, this layer, it obviously, because it is 16, it obviously has to take an input of 16 and it outputs 32 features. So it's like saying it is dot producting like this, like this. So here we're getting 500 cross 32, right? So the output of this will be this. Next we have this layer. So it's like saying we are dot producting it with 32 cross 64. And because we are dot producting, the result will be 500 cross 64. Then we have this. So it's like saying we are dot producting this with this, which basically results out to 500 cross 128. And at the very last, we are doing this dot product. So you can say that the last layer is taking 128 neurons, or it is taking 128 features, and it is projecting out only one feature. @1. And why I'm using @? Because @ means dot product. So you can think of the shapes as being dot producted. And this gives us 500 cross 1. Now, why 1? Simply because it is binary classification problem, and in binary classification problem inside PyTorch, always our output layers, this output features should be 1. That's why here it is 1. And then at the very last we should have our activation as sigmoid activation, which simply squeezes the value and brings it into a range of 0 to 1. So you can say that this is how the shape of this features is happening inside this neural network. And at the very last we got this. And then we create our forward function which takes these features and passes these features into this network or this model and gets the output and returns it simply. So once we created this class, we are creating an instance of this class. So using this neural network, and whenever we are calling this neural network, it is calling this init function. So it needs the number of features, and for number of features we are passing extend.shape of 1, which will give us our number of features. And that is how we are creating this model instance. Then we moved it to our device. Next we simply have our loss function definition as nn.bc loss. So here instead of coding our own loss, we are using the loss provided by this nn module, and that is how we are saving time. Then we use our Optim module to get an Atom optimizer so that we don't have to manually code the gradient descent logic for updating our parameters. Instead, we use this optimizer, which is very optimized, to update the parameters of our neural network. So this is how it goes. Optimizer is equals to optim.atom, and then we pass the parameters of the neural network, and then we pass the learning rate, which we defined earlier over here. Over here. Right. So that is how we create our optimizer, and then this is our training loop. So we run it for epoch number of times, and then at the very first we do model.train, so that we tell our model that alright, now we are going to train you. Next we are doing the forward pass. We are simply passing the train data to model and getting the y pred. And next we are doing the loss function calculation like this. So we are passing the y hat and the y train. Next we clear out the gradients, and then we do gradients compute, which simply computes the gradient of loss with respect to all the parameters of our neural network. And then we simply do optimizer.step to update these parameters so that we don't have to manually update them using the gradient descent logic. Instead, this optimizer handles it under the hood and it figures it out, and it does it beautifully. And at the very last, we are printing our epoch and our loss. And as you can see, this is how good it is converging. So earlier, when we did it manually, it was at the very first epoch, it was loss was 0.73, and at the last epoch it was 0.69. Whereas if you see here, at the very first it was 0.69, and at the 25th epoch it is 0.19. So you can see how well this loss is converging when we are using this optimized workflow. And that is why I am saying that whatever this NN and Optim modules are providing, they are highly optimized. So we should always use them instead of coding our own logic, and that will simply make the whole process much more stable and much more faster. And lastly, we have this inference. So model.eval. So here, just like we did model.train, here we are doing model.eval, and then we are disabling the gradient tracking. Then the same logic, we are basically doing forward propagation, then we do this, and then we are getting the accuracy, and then we are printing it. So it's the same logic which I have explained earlier, nothing new. So now also you can see that the accuracy is 0.5. Now why is it? So simply in our training data, while training, the loss converged in a very good manner, but still our accuracy is 0.5, which is nothing but a random guess. So the reason why it is happening is the model is overfitting, meaning that although it's performing good on this trained data, it is not actually learning the patterns inside that data. And that is why it is not able to generalize it properly on this test data, which is unseen data. So simply our model is overfitting, and there is nothing that we can do right now. But obviously I'm going to teach that also in the upcoming lectures. But you can simply think that our model is performing good on trained data, but it is not able to generalize well on our test data. So that is the concept of overfitting, which I'll discuss later in the upcoming lectures. But that is it for this optimized workflow using NN and Optim. And you saw how fast our loss is converging as compared to this manual method. So that's the magic of NN and Optim modules, which together makes the process of building neural networks and training them much more beautiful. Alright guys, so that's how you build your first neural network inside PyTorch. I've shown both the methods, like first building the neural network in an old school method, and second building the neural network using NN and Optim modules for optimized workflow. So I've linked down the code slides and also the notebook that we coded in the description below. And also guys, I've given an exercise, so please go ahead and solve it and make your concept stronger. And in the next lecture, we'll dive into another important concept, which are datasets and data loaders, which makes data handling much more beautiful. So take a break and I'll see you in the next one.